Start up the next set of discussion sessions, and the first one's going to be led by Sterl Phinney, observational tests of theory. So let's begin.
Okay, so I'm guessing this might be very short and we should give more time to the stellar binary for reasons that I'll explain. Nobody's made this joke, so I figured I really had to do it. CBDs are not legal in the US. So circumbinary discs, the way Ian and I divided it, I'll do black holes and everything else like stars that are not dead will be in the next session. So the idea was to see whether I guess the organizers said we were supposed to do observational tests. And so I think the difficulty with observational tests of circumbinary disks around black holes is first you have to find the binary black holes, then you have to find the circumbinary disk, then you have to characterize it well enough to test anything. And I'm not completely sure we've gotten to the first step. So that's why this session might be short. Around the supermassive black hole binaries, there's sort of several types of circumbinary disks that we've heard about. One is sort of on the parsec to kiloparsec scale, which is sort of part of the galactic merger process. We heard talk about that section already. Then when you get to the parsec scale, there's the question of whether to solve the final parsec problem, which is really a problem for 10 to the 7 solar masses and greater, and not for the LISA ones, of whether you need a triaxial galaxy feeding stars in, or whether you need gas assistance to get things in, or whether a third black hole coming in will solve the problem for you anyway. So it's possible that these are relevant to it. And then there's the question in the gravitational wave phase of if there is a circumbinary disk, could it be accelerating the contraction due to gravitational waves, or as Dong would argue, is it preventing the contraction? And there's a possibility that there might be electromagnetic counterparts to gravitational wave sources, pulsar timing, that we'll come back to in a minute. And then around the stellar mass black hole binaries, I think there's sort of interesting possibilities of circumbinary disks, which either could be from a binary which is undergoing very rapid mass transfer and losing mass from L2, or having a slow wind which is captured. So it's a binary system, but it builds its own circumbinary disk. Or as Max Mo has reminded us, almost all massive stars are in triple or quadruple systems. And so some of the time you could make 2 black holes with a fraction that depends on your beliefs in kick velocities and things, mass loss. And the tertiary companion would remain bound, eventually fill its Roche lobe or have a strong wind. And you could accrete onto the binary, and some of the time that could even be going on during a LIGO merger, and you can get an electromagnetic counterpart to a LIGO merger. And you can ask the question, have we actually seen any of these? I think any available time at the end can be devoted to SS433, which probably is one of these circumbinary disks, probably not a triple, but at least building its own from mass loss from the secondary star. And you could ask, well, maybe some of the high mass X-ray binaries, how confident are we that Cygnus X3 actually is 1 black hole instead of 2 in a very tight orbit? It's not very probable, but could we actually say that observationally? So it's possible we even know about some of these. Of course, you could also be accreting from the interstellar medium if you have a binary black hole, or as we heard, AGN disks. Okay, so maybe the first question for the audience is, do we confidently know any, we clearly know binary black holes, the Rodriguez system, PG0402 is clearly 2 black holes with jets 7 parsecs apart, but when we get to less than a parsec, do we confidently know of any? And I guess Scott Noble asked, audience show of hands, this is 100 years data on OJ287, which is supposed to be a black hole going through the disk of another one. producing flares. There's 100 years of data. Has a 12-year period, a precession period, which is just slightly longer than the observation time, so you can fit more better. Produces an impressive 20 billion solar mass black hole, and there's the data. So how many people are convinced that this is a binary black hole of 210 to the 10 solar masses? Okay, we got 3 hands up. Okay, good, good, good. Some of them are wobbly hands. Okay, so, as John Bacall used to say, you can bet, there's 5 sigma, you bet $100, 7 sigma, you bet your car, 10 sigma, you bet your house and the rest of your salary, right? Okay, so.
It's pretty low risk.
And another one, which I really like, is PG 1302 minus 102. It's a bit, I think that's about 20 years of optical data plus some more recent UV data, and it's pretty good. It's got past the minimum 3 wiggles. It's got to 4 wiggles and still going. And so how many people are convinced that this is a genuine binary black hole? Okay, Jotan, yes, okay, the authors of the paper must put their hands up, I think.
I think there's one more piece of evidence. That's the multi-wavelength evidence for PG 1302.
Hmm.
I'll say that without raising my hand.
Okay, would anybody like to suggest any more compelling candidates that I haven't put up there? I just picked those 2 because they're famous and I sort of like them. Yeah.
I think that the people who are working on OJ287 have put out some pretty interesting predictions for flares that should be happening when the binary crosses the accretion disk, and they've been able to predict them and then see them. So I think that that's compelling.
Actually, I would love, if somebody knows more about this, would love to hear more, because so the observation, as far as I know, was that they predict this orbit, 12-year orbit, crosses the disk twice every 12 years.
Mm-hmm.
And there was a flare, the recent one in the infrared, which was predicted with an error of only 4 hours in this model, provided you included general relativistic precession. So I find that either really good evidence or really puzzling, because this requires that some kind of simple toy model is valid to an accuracy of 4 hours divided by 12 years, which is 10⁻⁴ or 5. So that would be really good evidence, but it's only if you believe that this is a flat disk and the orbit is well, I guess the orbit is safe, but the disk would have to be completely flat. So I don't know. So I guess that's a criticism I have potentially, but I don't know. Do we believe that this prediction of 10⁻⁴ or 5 accuracy can actually be legitimate?
Yeah, someone who put their hand up. Given all that Kieran's also now said, why did only 3 people put their hand up? So what is so doubtful about OJ287 that people are worried about it might not actually be a candidate? It's not really clear to me, given the evidence that was presented.
Luke Kelly. I just think that there are still a relatively good number of free parameters and also a huge amount of noise in there. So the model definitely does not predict, every bump and wiggle in here. So it takes some interpretation of which of those components are real and kind of worth fitting with the model and which components are noise. So I think there's definitely wiggle room, although it is, it's getting harder and harder to resist.
This is Chiara Mingarelli again, and I totally agree with Luke. And my hand was halfway up, kind of wavering. And I feel like if this is going to be, the very first, potentially gravitational wave emitting binary, it's going to have to be astoundingly, good. You're going to have a really amazing signal. And so I think everyone's just being cautious. It's the first one, so you have to be careful. Also, in favor of this being a binary, when the authors are making these predictions, they included up to 4.5 post-Newtonian terms, like 4.5 PN, to make those predictions. Like, that's incredible. That's a really relativistic system. And so I think it's interesting, and I'm going to watch it, but I'm still kind of on the fence.
No, I would agree. I mean, it's very impressive how many PN, but as Zoltan said, it's still a flat disk. And as we just heard, it would be amazing if in a binary the disk were actually flat. So some of those parameters might have alternate interpretations, I think.
So, oh, okay, Jinnu on Zoom.
Yeah, so I definitely agree. This is a really impressive system. But what's really been puzzling me is, the fact that it does have like a century-long light curve, but a lot of the historical light curve didn't really have really high quality, and at least there has been some work suggesting that the long-term variability can be explained by no variability, periodicity at all. And on top of that, I think I'm really puzzled by the model that is, it's a blazar, right, with its jets almost pointing almost directly at us, and it has this secondary black hole punching through the disk that is orbiting the primary black hole, which is, I think, very different from what I've been at least hearing from this workshop. I don't know how typical that configuration would be, although it is just one single case. So overall, I'm not super convinced, but I will stay open-minded for sure.
Go ahead, Magda.
Okay, so I understand the light curve evidence can be is so-so, but I've been recently speaking to some people involved in the EHT. So if the EHT images this system, would that convince people?
Yeah, I was going to make a similar comment, because if you look at the binary orbit for this system, then at epicenter, it's 10 to 20 microarc second or something like this, and I think it's something EHT is looking at. What is unclear is the emission mechanism and what exactly you'd expect to see. So for very bright systems, you might expect that millimeter emission region to surround the entire orbit. So what are we actually looking for there that would tell us it's a binary? I don't know if anyone else has more comments on that.
Yeah, I mean, there is very nice VLBI that came out earlier this year on the 700 microarc second scale, which shows a jet wobbling around. But again, jets wobble around, so. Yeah.
So if it is really a binary, we would be able to detect it in gravitational waves with SKA phase 1. This is in Shin et al. 2021. So that's going to be an interesting test if nothing else is convincing before 2030.
And then Tamara.
Hi, all. This is Tamara. I just wanted to say that OJ287 or any other candidate that was discovered electromagnetically will simply just require some other type of evidence, in addition to the light curve or in addition to the offset broad emission lines or whatever was a way that, that this candidate was selected to begin with. So it's certainly a unique and striking candidate, OJ287, but in my opinion, in order for the community to be convinced, it will require some other kind of independent evidence. Not more of a light curve, but something in addition to it. So those are my 5 cents.
Yeah, I think that's an excellent point. I mean, I was going to list various other methods that have been proposed, and I think all of them are such that they're an interesting way of identifying candidates, but maybe by themselves, my guess is will never really give us confidence unless we get 2 or 3 independent approaches. All, if you found something with a variable light curve which had a micro lensing spike when it was aligned along the line of sight, you might go like this. If you saw OJ287 and you got gravitational waves in the pulsar with the same period, which will take a while because it's a 12-year period in precessing, it would be convincing. But yeah.
Yeah, Mark Avera. So I'm less familiar with the literature on OJ287 than I should be. But if it's binary, then the disk, even if it's equatorial, should have broken axisymmetry, like spiral arms or something like that. Do any of the predictions or any of the observations suggest that that the different parts of the disk that the secondary passes through are not the same, besides just turbulence?
I think the question is, just like in the stellar case, does the dust follow the gas? Does what's creating the millimeter emission, which is often synchrotron, is that following the gas, and do we expect to see spiral arms in that? So
I think it's also true, as was pointed out, there's a lot of wiggles and not all the peaks are the same, but in fitting the orbit model, you're ignoring some of the wiggles and picking other ones, and I think there's a lot of freedom. But it's definitely not a periodic clock, there's no question.
Yeah, maybe there's some gas physics in those wiggles, the other ones that we can pull out using circumbinary disk modeling.
Can I just ask? I'm not sure it's a circumbinary disk in OJ287. Please correct me if my impression is wrong. Because the secondary black hole is almost, the orbital plane of that is almost perpendicular to the accretion disk, right?
Yeah, no, I'm not saying this is not evidence of a circumbinary disk. This is just asking the question, do we know any binary black holes that might have first? So,
can I also take the prerogative to point out here? Yeah, Stefan?
Yeah, I think it's worth maybe adding infrared interferometry to the list that you had of applicable techniques. Like just a few months ago, the first mid-infrared image of NGC 1068 was published, showing basically classical the torus region. But if you observe in spectral lines, you can get higher resolutions to push it to the sub-milliarc second regime. And so it's just a big infrastructure improvement happening in parallel to allow you off-axis tracking, and this will be very applicable for AGNs to push it out to high redshift and then to search for asymmetries and motion in the photocenter shift of these lines for binary AGNs. So
yeah, that's a good point. That would be a sort of secondary addition to the quite wide binaries, but the sorts that you might see with accelerating BLRs or transverse Doppler shifts for the BLRs that would be on the milliarc second rather than microarc second level.
Yeah, but it's in addition to the spectral signature, right? You really get spatially resolved information. So it's another dimension in addition to the Doppler shift.
Barry?
So we may not confidently know any less than 1 parsec binary AGN, but depending on what PTA and Nanograph tell us in the next half year, we may be able to say something about the probability of occurrence of the number of less than 1 parsec binary AGN that we expect.
Yeah,
and that may help our.
Yeah, I think that will help statistically. I think I think in the near term, the difficulty of distinguishing what the mass function of the black holes, what the mass ratio function of the black holes, and distinguishing that from possible effects of either not solving the final parsec problem very well or solving it too well and getting acceleration. I think that will take a while to disentangle because it's just one number with as many parameters in it. But definitely, I think confidently seeing a background with the gravitation, with the Hellings-Downs correlations, and especially a slope when the slope comes out, I think will be a wonderful time, but still.
So this is Chiara Mingarelli again. I wanted to add to Barry's comment. So the work that Julie Comerford was showing the other day from Andrew Casey Clyde goes into, what if we take AGN as signposts for galaxy mergers, then what can we learn about the gravitational wave background? And then in turn, taking, as Sterl said, one number and decomposing it into its component pieces, you can learn about black hole masses, the redshift, and the minimum black hole mass that contributes to the gravitational wave background. Right now, what he's doing is that he's trying to find out how many of these AGN would really host binaries given the amplitude of the background. So that's a really great idea. And Andrew just presented his results at the Nanograph meeting right now. So I think you can watch the recording if you're interested.
Yep.
Savick word again. So just to add on to the idea of getting some idea of how many things that we might be looking for from the gravitational wave background, and then hopefully some of them are in AGN, although I agree that conflating activity with mergers is complicated and maybe not robust. But the another thing that we might do that's interesting is if there are stars that transit an AGN disk, and we have X-ray observations of that. And there are some examples of this where you have something that is clearly transiting the disk. There's about 10 known in the literature that are just serendipitous. If you have good timing resolution, right, that translates to very high, essentially angular resolution, and you can map whatever the disk crossing area is. So if there's some signal in the X-ray that there is some kind of binary or circumbinary disk, what that emission looks like, if there are enough of them, then we might be able to go and do targeted searches for that and try to map that emission.
Yeah, I think that's an important point, that the microlensing, there are two kinds of microlensing. They're microlensing by one black hole by the other, and then there's the traditional gravitational lensing of something at redshift of 1/2 in the front. And that already has told us that the disks are probably the wrong, at least some of the disks are the wrong size, and if there were 2 of them, that would be wonderful.
Yeah, sorry if this is maybe redundant a bit with what Ster, Chiara, and Julian actually already said in different ways, right? From the pulsar timing stochastic background perspective, I mean, you have to distinguish a little bit of about the signal, right? If you identify a single source and you can point it and find a counterpart, that's one thing. It tells you something about, circumbinary discs, the connection with AGN, whatever. But from a stochastic background itself, no. So really, there are too many things that are too degenerate with each other. If you measure the amplitude and the slope, you can get that in many ways. You can get the slope by stellar hardening, by gas hardening, by eccentricity. There's way too many things that are coupled together in order to infer specific information about circumbinary disks in this case, right? So really you need individual sources for that.
Let's see, what there's a, I think there's a
I
question.
have specifically on what Alberto just said, question, or to clarify. Alberto, so I guess just to clarify, the way that I was thinking about it is if you measure the stochastic background, then you know what the rate is of things that are merging, right? Or you have some constraint, and so then you have a better idea, for example, of how many sources or how large a volume you have to explore before you expect to see one, right? So for example, if you are relying on some detection mechanism in the electromagnetic where, just to take one example, like radial velocities of the iron K alpha lines, if those are closely attached to the individual supermassive black holes in a binary, and you can sort of watch them wobble, but you can only detect iron K alpha lines in the nearest 300 AGN, and you expect to need to survey at least 10,000 before you find one binary, then, you can put that one in the trash or, ask for a much bigger, better telescope.
before you expect to see one. So that's kind of, am I misunderstanding what we'll learn from that stochastic background detection?
Well, I think I will guess what Alberto will say, and then I can check whether it's right. So the problem is that if you measure an amplitude, you can't tell whether it's a few 10 to the 10 solar mass black holes or a huge number of 10 to the 7, and then you still don't know how many to look for.
Gotcha. Okay, thank you. So actually, I think that, if you have a certain underlying black hole mass function, Savik is totally right. You have a number density of sources, and then from the continuous wave limits, you go out to some volume, and then you say, well, should we have already found something there? There's one supermassive black hole binary population that is building up redshift slice by redshift slice, the gravitational wave background. So if your amplitude of the background tells you that you should have 5 times 10 to the minus 6 supermassive black hole binaries per megaparsec cubed, then as you go out in redshift, you do expect to start seeing 1, 2, 5, 10, 18, a million. So I think that Savik is totally right. And in fact, that's a cross-check that we're doing right now in Nanograph to make sure that there's a consistency between the amplitude of the gravitational wave background and the current non-detection of individual supermassive black hole binary systems, because after all, there is just one underlying black hole binary population.
Oh, okay.
I want to go back.
Alberto can respond to that one, I think.
I guess
what's controversial about that?
No. Well, I think here is, what do you mean by non-detection of a single binary system?
Upper limits.
But you mean from PTA or from other observers?
From pulsar timing. So say that the current Nanograph upper limit is that there are no, 10 to the 10 supermassive black hole binaries within a gigaparsec. Right. So these will change as a function of mass and distance, given the strain. Right. There's an upper limit on the strain. And so you can then, if you have a given black hole mass function, go back and figure out how many binaries should there have been given the number density of sources that you predict from the amplitude of the background. These two things have to be consistent.
Right.
So yeah, I don't understand.
But there's no parameters in you think the black hole mass function is known, the mass ratio distribution and the mass function of merging as opposed to non-merging black holes are all known?
What we found is that I wanted to get back to the original AGN point, which is why I have the microphone in the first place. But I'm happy to talk to you all about this too.
There's still some other comments on this. I think we should maybe make sure we hear from a couple other people too.
I mean, I think that's kind of an unfair argument. It's like saying that there's one standard model of physics, so why can't we just predict the gravitational wave background? I mean, there are just so many steps that you have to go from the black hole mass distribution, then to a gravitational wave spectrum, and then individual sources. Like these different types of models can all produce the exact same gravitational wave background spectrum and still have a completely different population. So you can leave the mass distribution the same, you can leave the galaxy-galaxy mergers the same, and just change the evolution parameters or the accretion parameters, and then completely change the distribution. So I think it's really a kind of an unfair oversimplification to say that there's a single mass distribution, so then you can infer everything. I mean,
well, we all know that there's a lot of favorite black hole mass functions out there, and there's different ones, and you can compare them, and they all give similar answers except at the very high mass end. I think my colleague Andy Goulden calls this the wagging of the tail of the black hole mass function, but we don't expect the majority of the population of supermassive black hole binaries to come from that very high mass end, right? We do expect. Of course, there's other parameters. We have lots of models, but I think if you have a given model of the gravitational wave background, that you should be able to make self-consistent predictions for both.
Okay, we've got we got another comment here too.
Oh, I have a completely different topic, I guess.
Go ahead.
So these different gravitational wave instruments kind of favor one type of source over the other. For example, in my project with Kiara and Jeff, for our gravitational wave strain calculation with Hassasiyah, it kind of disfavors supermassive black hole binaries with extreme mass ratios. And also with my project with Zoltan, most of the LSST sources that would slowly evolve into the LISA would be ultra short period. So I guess a general question would be if we favor sources with a particular type of property? What about the other ones except E&M signatures? Do we just have no hope for them in gravitational wave detections?
Yeah, so maybe that's a good introduction. So maybe we should, since the object of this was testing theories of circumbinary disk evolution, not testing theories of black hole mass functions by PTA, maybe we should move on to other topics. I just flashed this up for people to stare at. This is, I think, was a diagram originally made by Jeremy Schnittman about a decade ago, and I've been gradually adding stuff onto it ever since. So these are all the ways that people have proposed for finding evidence of binary black hole mergers, you know, X-shaped radio lobes and C-shaped radio galaxies and so on. The dual AGN tidal disruption comes in, funny SEDs with the gap between the mini disk and the circumbinary disk with the missing region of radius in between. Julian worked on that, for example. Off-center Doppler shifts, X-ray flares, and so on. So, let's see. I guess we've done this one plenty. I thought maybe it would be worth saying one thing, which I think is missing in a lot of the simulations, which are scale-free, and the assumptions are probably great for the binary stars and maybe not so great for the AGN disks, which is ignoring the effect of radiation. So the canonical, everybody's favorite Seyfert galaxy is 0.1 of Eddington, but that means it's 10 times Eddington for the dust plus the gas. And so the question is, what happens to the gas before it gets into when it's still in the circumbinary disk and not in the mini disk? So a little bit of mini disk luminosity could have a big effect on the accretion rate. And there's some nice, I don't know if Stefan Hernig is online or not, might say something about this. This was one of the first simulations that sort of included the effect. So this is with no this panel is a time sequence with no radiation, and this one is with the radiation turned on. And you know, instead of 2 accretion disks, you get 1 for a while, and then you get nothing. Yeah, Julian.
This is identical to
This is essentially the identical problem to one that affects single AGN, the famous support of the obscuring torus, which is likewise largely, it was mostly thought likewise to depend largely on this sort of radiation force on dust and causing outflows. But nonetheless, despite the outflows, the system still accretes. And the likely picture is that at large distance, outside the dust sublimation radius, the inflow rate is rather larger than the AGN needs. A bunch of it gets blown away. A fraction is captured, evading these radiation forces, and then it continues on inward.
Let's see, Kimi.
Okay, so I'd like to share our basic idea of radiation-driven warping of a circumbinary disk around supermassive black hole binaries. And you can see the schematic diagram of a triple disk system, which composed of 2 of mini disks surrounded by circumbinary disk. And here, orbital plane is misaligned with circumbinary disk plane, and the force of radiation coming from mini disk can affect dynamically on circumbinary disk, and which causes disk warping. And original idea of radiation-driven warping from single radiation source was given by Pringle in 1996. And we can obtain radiation warping radius by solving the simplified diffusion equations with tidal torque and radiation torque of specific angular momentum of circumbinary disk. Could you, yeah. And that is derived theoretical warping radius as a function of the semi-major axis. And here we introduce a Bordeaux hypothesis that the central object is central object of major disk in NGC 4258 is binary black hole. And also the major disk warping results from radiative force, results from radiation-driven warping. And then equating the theoretical warping radius with observed warping radius, where which is assumed to be a major spot radius. And then we can evaluate the semi-major axis of binary black hole, like 0.03 parsec for NGC 4258. And I know there are a lot of caveats to demonstrate this hypothesis, but I hope our model is a good step to consider this scoping mechanism of a circumbinary disk as a missing physics and testing observation of testing theory of circumbinary disk argued in this conference. Thank you.
Yeah, thanks. So I think the message I thought of three things. Maybe others can think of others. There's the effect on dust that we already discussed. There's the radiation-driven precession of the disks, and there's mass loss from the mini disk itself, which means that neither mass nor angular momentum are strictly conserved if there's a jet or wind from it. Yes, Roger.
So I was just going back to the last session, and it's really a question of physics rather than observations, but in this scheme of radiation pressure providing a torque to warp a disk, don't you get much more stress from ablating the surface to an outflow?
So, sorry, could you speak slowly? And
sorry, in this scheme of using radiation pressure to exert a torque on the disk, which you described, don't you get more stress from ablating the surface as a slower moving outflow of gas?
This question is, if you had a wind from the disk rather than just reflected radiation, could you get a larger torque?
Get more momentum per unit energy. Anyway, this is a physics question.
Okay, so let's talk, have a discussion later.
None of the modelers are enthusiastic about putting all the radiation effects in there. Okay. Yeah, so I had one quite suggested question, which is if we could talk about the lump, which I think Scott Noble emphasized in his talk. So this is the lump, the m=1 lump, which I think is seen in simulations for Q greater than around 1/2, but maybe not less than 1/2. And if one were interested in like the light curves we were talking about in the beginning for orbital modulation of the light curves, the lump produces a modulation in the accretion rate onto the mini disks at 1/5 of the orbital frequency. And perhaps if one saw a modulation at either 1 or 2 times the orbital frequency and something from the lump, maybe you would have more confidence that you were seeing or you saw the beat between them. So the question that was asked was, did any of our stellar colleagues where the same physics ought to happen, is there any evidence of this in the stellar binaries? Which means that we should look for it in the supermassive ones.
Looks like Ben wants to say something.
Hi. Yeah, so the best stellar case to look for this is B4046 Sagittarius. It's a 2-day circular binary. But the problem there is that we don't, the observation to probe the inner part of the disk is very difficult to make. It's much easier to take time series images and measure the mass accretion rate. To actually probe that inner part of the disk requires time series near-infrared spectroscopy, which is expensive to get and really hasn't been done. But that's potentially something that we could do to look for this M1 lump. And given that the period's only 2 days, it's feasible to actually observe that thing orbit. The only kind of caveat I'll say is that B446 doesn't actually show that 5 orbital period sawtooth pattern. There's kind of too much stochastic variability that we see on top of it. So I guess I'm concerned whether that stochasticity in the accretion rate is kind of draining that structure in a kind of a more random way. So that's kind of the stellar side.
I don't know if this is relevant. There are objects that I've always been puzzled about whether that had something to do with effects like this. They're called DPVs, or double period variables, and I don't quite know what they are. I don't think anyone really knows. It's not this is not twice the orbital frequency, it's 30 times the orbital frequency. I want to throw that out there because I think it's these things deserve more attention from some of us at least. They're ongoing mass transfer, so it's not unlikely that there's material out there.
Please go ahead.
Yeah, just a quick question about this picture I see. I'm surprised you see the same power, 1/5 of the orbital frequency and twice of the together same time. I'm just we never seen this kind of thing.
Well, you could ask the authors are
here.
Yeah,
I'm surprised. I don't, when we have a simulation that resolved the cavity, what happened to this thing? Why do you see?
He wants to know why the power is the same.
You see this? Yeah, you have this same power. Yeah, similar power. Let's say 1/5.
So which one is bigger in your simulations?
Yeah, in the circular orbit, it's 1/5.
Which one is bigger though? This one or this one?
The 1/5 frequency.
This
yeah,
one
this one.
yes.
Never seen.
Well, I don't know, Scott, Julian.
Yeah, I mean the relative strengths of those peaks, we actually don't see in my calculations. We don't see too much power at 2 times the orbital frequency, but it depends on mass ratio. Also, it's not clear that the lump is the same in MHD simulations and in 2D viscous hydro simulations. I think we need to make a closer comparison between them.
The only additional comment I'd make is that the twice orbital frequency is certainly a special property of the equal mass system. That's where the twice the orbital binary frequency comes from.
Yeah, I mean, otherwise it's here. But
yeah.
I just wanted to comment on imaging attempts maybe to find that lump, right? So the problem is that we often have only continuum observations where we see that there is some excess in the upper astron position of such rings around binaries with ALMA, but this could also trace this traffic jam effect and doesn't represent the gas density that is often simulated there. So it's difficult to separate the two things unless we have real good gas density traces that are difficult to get at this high, very angular resolution that you need to probe that region.
Okay, I'm being reminded that we need to wrap up for the next session. I thought I had a couple more slides. I'll just flash here. Jotan, I don't know if you wanted to say a couple of words about spiky.
Yeah, I guess this, I don't want to give a mini talk here. Was already mentioned that the one black hole can be lensing the other. So we have a toy model prediction in the previous slide, which I think maybe you can go back for a second. So this is from postdoc Jordi Davila at Columbia, and we just painted a emission of a binary, and you see on the top that when it's passing, one is passing right behind the other. You actually see two images of the receding one in red, and the blue is the approaching black hole. So this is what, and then you don't resolve this, so you add up all the emission, you should get these flares, which are periodic, obviously. The feature we actually were amused by here is that you can actually see the shadow, because when you place the shadow of one black hole right behind the other, there's a dip on top of the flare. This is just a cartoon prediction, but maybe then it's nice to connect this to another binary candidate, which was not in the top 2 of Sterl. I guess it's the bronze medal for a binary. So that's something in the paper involving then also some others. We called spiky, and then maybe you can go back to the next slide. You see the light curve of this object. So this was brought up already. This is a rare case where Kepler actually saw a quasar, AGN, rather than a planet. So it has extremely high cadence light curve, and you can see what it looks like. There's a large flare, and that curve that you see on top of it, on the top panel, is basically a Doppler modulation of an eccentric binary, which fits the overall shape well. And maybe the most exciting part is when you blow up the spike, the simple lensing light curve fits very well. It's maybe an unusual shape. It's very symmetric. And then this I don't want to say in print, but I mean, if you look on top of the flare and you zoom in, there may be even a hint of a dip on top. So I don't know, another candidate. And then maybe you can say something, because in principle, this is confirmable by seeing recurrence of these flares.
Yeah, and I'll just note too that this isn't just a periodic variation, this and the Doppler together. They're not just a special shape, but there's kind of a parameter-free wavelength prediction that once you have this shape in one wavelength, you can predict what it will look like in other wavelengths. So it's a little extra than just photometric variability with an interesting shape.
I guess that's including some disk profile.
And that is, yeah, that's twiddle, no extra parameters. There can be, we can discuss that later though, because we're running a bit into the next discussion session. So I would suggest with maybe a final conclusion, we move on.
Okay, well, the last slide, I'll just flash up because I think we can talk about this all next week. There is one system which really has everything. The Swiss watch of the sky, jet 0.26c, wind 10 to the -4 solar masses, circumbinary discs. They're all precessing, they're all orbiting, wonderful system. And so in contrast to the AGN disks, I think the ones where I think there's probably the most hope of actually testing theories of circumbinary disks are, again, in the stellar mass black holes like SS433. And I think Catherine gave me some slides, but I think she's giving a talk next week, so we can all learn more about SS433. Okay, next up.